Hi, thanks for joining me. In this video, we're going to talk about the procedural standards of making pressure measurements. And in previous videos, we've looked at exposure errors and also the quality assurance. In this video, we're going to talk about how an ASOS calculates and produces pressure measurements. In the United States, weather observations are made by Automated Surface Observing Systems, or ASOS. And for pressure, the ASOS has a pressure transducer called a Cetra 470. And from that, we can calculate station pressure, sea level pressure, altimeter setting, pressure altitude, and density altitude. Station pressure is the atmospheric pressure computed for the level of the station elevation. More or less, this is the atmospheric pressure that's at the elevation of the barometer. If you live on top of a mountain, and the mountain is 5,000 feet tall, then your pressure is typically going to be someplace near about 850 millibars. Station pressure is calculated after all errors are eliminated from the pressure reading. Sea level pressure, on the other hand, is the atmospheric pressure at sea level. That's either measured directly if you have a station right at sea level, but most often it's empirically determined through calculation using the observed station pressure. Most stations that make pressure measurements are not located at sea level. They'll be at different altitudes, so we have to figure out a way to get pressure for sea level. This is typically done through a calculation. The reason that we need sea level pressure is so that we can compare pressures at various locations. If we just plotted on a chart the pressures at the surface of the Earth, you would always see a low pressure system in mountainous areas and higher pressure at sea level along the coasts. So we need to come up with some method to reduce pressure to sea level. We do that using an equation. And first we have to define some variables for this equation. We're going to call ZST the height of the station. Of course, 0 is your height at sea level. PSL will be the sea level pressure, and PST will be our station pressure. The equation that we're going to use is the hypsometric equation. This is one that relates the thickness between two pressure surfaces to the temperature that's in between those pressure surfaces. The equation has in it the gas constant, gravity, temperature, the virtual temperature, which takes into account water vapor, and also pressure, two pressure surfaces. We can rearrange this equation, here's the algebra for it, to solve for the height of the station. If you look at the difference in height between two pressure surfaces, if one of the heights is 0, that just leaves us with the height of the station. And then algebraically solving for the pressure at sea level, we can see that we end up with a function that's exponential times the station pressure. What we know in this equation is the height of the station, the pressure at the station, or station pressure, which is measured by a barometer. We also know the gas constant, that's a constant, and also gravity, not necessarily always a constant, but sometimes we can assume it's constant. So in solving this equation for the constants, we can raise e to the g naught, zst, and rd. All values there are constant. As I said, gravity is not always constant, but we're going to assume it's constant here for a given elevation. And with that, that leaves us with a couple of variables. We're left with the pressure at the station, station pressure, and also E raised to the 1 over T, and that T is temperature. Specifically, it's virtual temperature, accounting for some water vapor in the atmosphere. But we're just going to assume that that's just temperature. Now, that's the average temperature in a layer. So the equation gets kind of simple. Measure the pressure at the station. We multiply it by a constant. But then we've got this E raised to the 1 over T, and that's where things get kind of complicated. This temperature, what is this temperature? It's the mean virtual temperature from the station down to sea level. But we're talking about rock. What's the temperature of rock? Well, it's not really the temperature of rock, but the temperature of the air underneath the station if there was no rock. If there was air underneath this station, what would its average temperature be? And there are a number of ways to figure this out. To figure out the mean virtual temperature in the layer, what you need to do is average the temperature in the layer using some lapse rate and also some surface temperatures, and then also correct it for moisture. And then finally, there's one other thing called the Plateau Effect, which we'll talk about in a little bit. So the temperature in the layer, the first one, the temperature in the layer is typically an empirical relationship using some lapse rate. Typically, it's the standard lapse rate that might be modified a little bit. Typically, it is modified for each station. And then you take the surface temperature over a 12-hour period and average that so that we get rid of the diurnal effects. You know, in the morning it's cold and in the afternoon it's hot. If you just use the cold temperature, you'll get higher pressure. If you use the warmer temperature, you'll get lower pressure. So averaging the two eliminates the diurnal effect. Moisture in the atmosphere, in that layer below the station, it's kind of hard to estimate. You know that moist air is less dense. Typically, they don't really account for moisture in that layer of air. And then finally, plateau effect, they found at elevations above 3,000 feet that over a period of time, sometimes the calculations of station pressure are different than similar pressures in the area. So they come up with an empirical relationship to bring the pressure to comparable annual averages of sea level stations. The inherent problems with this equation is that you end up with some errors because you're making some big assumptions. And the biggest errors tend to be where you have to bring the air down from high altitudes, or meaning mountainous locations. Because, of course, this calculation is a strong function of temperature. And where you have cold layers in valleys, you tend to end up with higher pressure. Where you have warmer temperatures near the ground, you end up with lower sea level pressures. And then finally, we've got this plateau effect, which tries to reduce these errors. So you need to be really suspect of pressures where there are large changes in temperature. When you see large changes in temperature in the past 12 hours, sea level pressure may be suspect. And then also in locations where the atmosphere is not hydrostatic. We won't talk about that, but that's typically near thunderstorms or in strong downsloping winds and mountain waves. This is the algorithm the ASOS machine uses to calculate sea level pressure. It takes the station pressure, multiplies it by the pressure reduction constant. We talked about that constant already. And then multiply that by R, and R is the pressure reduction ratio. And that's what accounts for temperature, plateau effect, and other factors. And then finally, multiply it by 33.864 because the pressure transducer reports pressure in inches of mercury, and that needs to be converted to millibars. So I know that's kind of complicated, but that gives you some insight on how sea level pressure is calculated from an ASOS station.